know this about the brain? We're making large judgments about things that can occur in the brain, and how do we even know? Well, there's different types of brain imaging techniques, or not so imaging, but brain mapping techniques, if you will. There's two that really occurred in the 1920s and before, and those were ablation, or removals of brain parts, as well as electroencephalogram, also called EEG. Then we had a blossoming of brain imaging technology in the 1960s and 1970s, including CAT scans, often called PET scans, and MRIs. And then in the 1990s, we had the development of MFRIs, and beyond, we're now into many more advanced techniques, but one of the advanced techniques we'll talk about is DTI. So when we refer to ablation, what we really mean is removal or dissection of brain material. And this has occurred in many cultures around the world for many thousands of years. The image displayed here is from Inca and Aztec skulls, showing that there was removal of parts of the brain. This could have been to a brain tumor. We know there's been lobotomies done in the last 150 years where people would take and remove parts of the brain to help calm things like depression or schizophrenia. And of course, removal of parts of the brain due to epilepsy and really severe seizures. So ablation can refer to removing or cutting out of brain tissue. More modern techniques might include freezing, cryogenically ceasing activity in part of the brain, or through laser surgery. And so ablation, when of course it starts out, it's going to be trial and error, and that's how we learned most of the early things we know about the brain. Then in the 1920s, we developed electroencephalogram technology. And electroencephalogram technology, a lot safer than ablation for non-clinical participants. And what it includes is wearing this cap in many cases, in which a person has lots of different little receptors. They wear gel on their hair that helps to conduct electrical impulses. Now keep in mind, our nervous system is an electrical system, so when the neurons in the brain fire, they are releasing electrical signals, and the electrical receptors in the cap pick up those signals. And for many decades, this was the primary way we read brainwaves, and so it would be on a very you get this printout of different waves, different brain waves, look like little squiggly marks on a paper. And what you would learn is how to interpret them for ERPs and different nodes of the brain. And it took a lot of advanced training to learn how to read EEGs. Now we have computer software that will interpret it for us. And now you can even get commercialized software, such as things like the Muse headband, which we'll be displaying in a future unit, which now, instead of having gel and suction cups, it's just a headband that goes on that has a couple receptors right at the front. So one of the things about EEGs we should note is it had good temporal resolution. That is, when things changed in the brain, we could track it second by second, or even smaller than a second. So good temporal resolution, but poor spatial resolution. For many years, researchers had to guess kind of where in the brain these waves were orienting or originating from. Then in the 1960s, with the development of computerized tomography, things became a lot more advanced. This is the first time we could really make a picture of the brain. So this is often referred to as a CAT scan. Most local hospitals and small town centers have a CAT scan machine or two. And this is where a series of x-rays are used to quickly generate structures and to spot abnormalities in the skull. And so this can be used to see brain tumors or brain tissue damage. It can also see if the ventricles are swollen, or meningitis, if you will. It can't really denote the differences in gray and white matter too precisely. It's still a pretty rough picture, but it can definitely help us. We can definitely see if there are major structural issues that may be causing psychological phenomena in the brain. Something much more advanced than CAT scan is the positron emission tomography, often called a PET scan or PET. And so this records, rather than X-ray, it records blood flow via radioactive substances that are injected through the bloodstream. So before you go in for a PET scan, often you get an injection, and these radioactive isotopes are tracked in your brain. And what happens here is we can see which areas of the brain are used more heavily. So the radioactive isotopes will light up the areas of the brain that are most active. So it's not showing structures of the brain, it's showing brain activity. So you won't really find if things are a different size in the brain with a PET scan, but it will show you which areas you're using. And some of the neat ways we've seen this is people with dementia tend to have their areas light up less the more advanced their dementia becomes. We also find that people currently undergoing a major depressive episode, their brain will light up less than when they are not in an episode, or if they're in a manic episode. So we can see how different areas of the brain will light up. So this has good spatial resolution. We can see where in the brain the activity is stimulated, but it has poor temporal resolution, and that's because there's a lag in the communication of the isotopes and the imagery. So it does show the activity using tracers, which is really nice, but it's not perfect. It did make it to a lot of breakthroughs, and you'll still see PET scans used today. There are researchers that still use it today and still publishing journals with this technology. It's still helpful. Then we have MRI, also known as magnetic resonance imaging. And so this uses magnets and radio waves to create a very detailed image of the brain. This is one of the most detailed structural images of the brain. It doesn't show brain activity, but it does show structures. And we can see here, we can see the limbic system, we can see the brainstem, we can see the sulci and gyri of the cerebrum. It's becoming a lot more advanced. And so this doesn't have any temporal resolution. It's just a static picture of the brain, but it has really good details of the structure. So if we're trying to find some sort of abnormality, even trying to map the size of the amygdala, we can do that with the MRI. Then we have, in the 1990s, we advanced the MRI technology to include functional MRI. So functional magnetic resonance imaging is where you take an MRI scan, but over top of it you overlay a blood flow map showing the resources used in the brain. So this is different than the PET scan. Instead of tracking radioactive tracers, we're now tracking oxygen, and it doesn't require injection. So the FMRI is great. It has good spatial technology because it has this really advanced mapping of the brain. Still has a bit of a temporal lag, of course, but getting better. And so for many decades, from the 1990s until very recently, this has become one of the most cutting-edge types of brain imaging, brain mapping that we have. Most large-scale Canadian universities, if they're lucky enough, they'll have an fMRI scanner, and that's really where we see top-tier neuroscience papers come from. It's from fMRI scans. And so this allows us to have a person do an activity, and you see which areas light up for the activity, and you can also see what structures are used. So it's really good. Since the fMRI, there's been many other technologies emerge, and they're picking up pace at different rates. One of the newer technologies that seems to be the most promising and seems to be breaking through the most is diffusion tensor imaging, or DTI. And so what this does is it traces water to show the connections between regions. Rather than just showing which areas light up during an activity, it actually shows the networks and pathways with which the water flows through. So instead of showing, oh, this area is lighting up, now this area is lighting up, it'll actually show where the water originates from. So because of this, it has good spatial and temporal resolution. So it's a little bit harder to interpret here. What you can actually see in this image is the water moving through. Very fantastic imagery now that we have more advanced computer software, of course. And so what you can see is the pathway the water goes to. So we almost start to see the circuits in the brain, or the pathway of where the neurons speak to each other. And so this has really been a remarkable breakthrough, going all the way back to the EEGs. So still today in Canada, we often have EEGs at most Canadian universities. A few of the larger ones will also have fMRIs. And I believe at U Calgary, we now have a DTI at the Cummings School of Medicine. And so it's remarkable to see this shift, even over the duration of since I've been an undergrad.